this says number 6, but it's supposed to be number 11. We have this sphere, it's electrically charged, and we want to know what the free body diagram is. So here, this one's not going to work because clearly the vertical forces are unbalanced here and here. And here. I need to be careful because it looks like, if I'm clear on this, let's just double check. So when I take this line here, I draw it, it clearly doesn't balance. Whoops, it clearly doesn't balance the vertical component. So this vertical line here is clearly too long to balance the vertical component of this force here. However, if we go to part D, this vertical line here is clearly able to compensate for the vertical part of the upward force here. So choice D is our correct choice. And as far as horizontal goes, once again, this horizontal line here, let's just double check. Like if we draw this, the horizontal line here, we need to make sure that it can balance on the other side. So when we go with this arrow, yep, the horizontal balances, whereas here, it's just a little bit too long. So this tension here isn't big enough to compensate for the electrical force or the gravity. So choice D is the right choice. Now for number 12, we've got an elevator, and the scale reads 12 kilograms. We get 10 kilograms resting on the scale. Oh, how mean of them. They give us mass instead of weight. So let's be really clear. The weight is 100 newtons. The scale would read 120 newtons. So let's just be clear on this. So we've got weight minus the scale reading equals m times a. So we've got 100. And actually, let's get this reversed because the weight reads down, the scale pushes up. So we've got scale minus weight equals m times a. So that's going to be 120 newtons minus 100 newtons, sorry, because it's 10 kilograms, equals 10 times a. So I'm getting 20 equals 10 times a. And so that's going to give me a is 2 meters per second squared. And since the scale reading wins, that means this is going to be 2 meters per second squared. Sorry, 2 meters seconds to the negative 2, pointing up. And then 13, a truck hits a car. We want to know how the truck force on the car compares to the car truck on the force, or the car force on the truck. And this is just a B. It's Newton's third law. B, equal and opposite always. Now here we have an object moving in a circle. Which way do things point? Let's be clear. We can rule out A and B because acceleration needs to point towards the center. Now here, if V really pointed towards the center here, then this thing would fall towards the center. It actually turns out this is why circular motion works the way it does. V is always tangential to the circle. A pulls it towards the center, and that's why it doesn't shoot off like this, but rather it curves in a circle like that. So choice C is correct. And for 15, this is a tricky one. This is a really mean problem. Let's actually work this one out. I'm going to do a quick version of this, and this is something we'll work on a little bit more next semester, so I'll call this the positive direction. So I've got tension here, little mg here, and big mg here. And I'm going to define this way as positive. So I'm going to have mg minus the tension equals big M times A. And then T minus mg equals little ma if I'm keeping the sign conventions consistent. So let's isolate. Here I'll have T equals ma plus mg when I isolate. And I'll substitute that back into here. So I'll have mg minus ma plus mg equals m times a. I'm going to need to simplify the algebra. When I do that, I'm actually going to end up getting mg minus mg equals m plus m times a. In other words, a is m minus m times g over m plus m. And that choice is choice A. All right. The momentum of the system is conserved if there are no external forces acting on a system. If you remember, we had internal forces, which are those collision forces that acted on the objects. And then for 17, two spheres moving towards each other. The spheres collide. the total change in momentum of both the spheres, the total momentum change, should be 0. In other words, the total momentum of the system never changes. Individual momentums will absolutely change, but the overall total momentum of the system change should be 0. The velocity of a particle is changing, the rate of the momentum of the particle, the rate of change of momentum of the particle. This is interesting because we actually talk about impulse being the change in momentum. So the force is going to be delta P over delta T. In other words, the net force is the rate of change of momentum. So then for, sorry, 1 second. And then for number 19, we're going to have this problem here where we have a car hitting a trolley, and 4 kilograms here, 4 kilograms here. Now, we need a total momentum of 8 Newton seconds, and so we got to look at all these. So this one, we've got 16 Newton seconds because 8 times 2 is 16. This one is 0. This one is negative 8. This one, though, it's 8, and let's look at why it's also correct, because this is 0, and then we have 8 Newton seconds here when we multiply it out. So that's how we're getting 8 for that. And then for number 20, we have a force and a time. What's the impulse equal to? At this point, we should know that impulse, J, is going to be force times time. So that is our impulse. So these are the videos for 11 through 20. I'm going to post these. I got these done at about 12:15 today. What's going to happen now is I'm going to post these today at 2:30 in the afternoon. And any of the boys that took the test yesterday, you can either come by after school today, or what I'm going to do is I'm actually going to scan your sheets that you did your multiple choice on, and I'm going to actually email them to you individually along with a link to the Haiku thing that has the solutions worked out and a blank test.